Okay, good morning, everyone. Thank you very much for joining us today on this webinar. My name is Shaji Khan. I'm an applications engineer at Hydra International, and my job is to help you design and install efficient grit removal systems. In this presentation, after a brief introduction about Hydra, we will look at the problems that are caused by grit, the science of grit capture, and how Hydra International can help you design and implement effective grit removal systems. Did you know that wastewater treatment plants spend hundreds of thousands of dollars on preventable grit-related maintenance costs? Preventable is the operative word here, which means that grit removal, when applied correctly, can help you save hundreds of thousands of dollars. Hydra International is a solutions provider for a variety of water and wastewater applications. We are headquartered in the UK with offices in the US, Middle East, China, and Australia. We have a network of distributors and partners all around the world that help us reach customers in over 40 countries. We have over 37,000 installations worldwide, and we have been in operation since the 1970s. As a company, we operate in various sectors, but today we will focus on grit removal from municipal wastewater. Hydra International is the market leader and pioneer of many grit removal technologies since the 1970s. We offer proven technologies and have featured in academic literatures like Wastewater Engineering by Metcalfe and Eddy. We have also worked with universities around the world by performing in-field testing and proving the efficacy of our solutions. We have our own test labs in the US and UK in which we test and verify our research during product development. Let's talk about grit and why it is a problem. Well, grit is a nuisance material. Anyone who has been to the beach can attest to that, right? And it is no different for wastewater treatment plants. It adds no value to any part of the treatment process. It is undesirable and it gets everywhere. Literally everywhere. Wastewater treatment plants are significantly impacted by grit. It causes abrasive wear to mechanical equipment, increasing maintenance and operational costs. And it accumulates in processes throughout the plant, reducing processing capacity and efficiency over time. And once grit is spread around the plant, it is an expensive problem to fix. Grit accumulation comes with several new maintenance challenges. You must take the process and vessel offline and send someone in there to clean it, often manually. This costs time and money. It is important to note that all these pictures from different plants did have some form of grit removal system, and yet grit made its way into the plant. Our research says that most operators have a grit problem, but they don't do anything about it. The assumption is that grit removal systems were installed, but the grit still made its way into the plant. So it is inevitable. There is nothing we can do about it. This is an incorrect assumption. The problem is preventable. We just need a system that works. The picture that you just saw were a result of less than 50% removal of total grit that enters the plant. The solution is a system that removes the bulk of the total grit load. We know that grit affects all areas of a treatment plant. Let's look at some figures. In our research, we have estimated that potential maintenance costs due to grit is around $9.2 per 1,000 cubic meters of wastewater. Now, granted, in your specific market, it may cost less to clean an aeration tank, but it might cost more to replace the pump. On average, this figure is representative. That's $9.2 when we're targeting only 50% of the grit load. If we capture 90% of the total grit that's entering the plant, it will reduce the grit load to a fifth or an eighth, which will also reduce the grit impact cost to $1.8 as compared to $9.2. This might just save you up to $8 per 1,000 cubic meters of water. Clearly, there is an advantage in removing more grit at headworks. Let's look at an example. We've collected this cost data from conferences, research papers, and from plant owners around the world. This is an insight as to how much money was spent in fixing problems arising due to grit. We turn the cost into cost per volume of water treated by taking into account the average flows of various plants. As you can see from examples, plant number 2 paid $500,000 to clean up and fix their primaries. Plant number 5 spent close to $250,000 to clean bioreactors every 8 years. This is just a summary of areas that our analysis covers. We use the removal efficiency for the various technologies based on relative performance data. From that data, we created a total cost comparison for a 22 MLD plant. And also listed here is individual cost of grit for different areas in an STP. And if you take a difference, this slide shows that Hydro can potentially help you save over $100,000 per year in maintenance cost in a 22 MLD plant STP. It is important to mention here that it's not just the maintenance, but also operational costs that we help save. For example, our analysis shows that we can help save $10,000 per year in just energy consumption by reducing grit load on aeration basins. In our estimates for a 22 MLD STP, Hydro can potentially help you save over $2 million over a 20-year period. And the savings in 5 years, which is equal to $512,000, could cover the cost of a new advanced grit system for a 22 MLD plant. In other words, the system pays for itself in 5 years. So grit removal is important. Our objectives in removing grit are to prevent abrasive wear on mechanical equipment such as pumps and centrifuges. Preventing grit deposits in aeration basins, digesters, and piping is also another objective. All this would save significant sums of money. Let's talk about why almost half of the total grit makes its way into the treatment plant and is not captured by conventional grit removal systems. All grit removal systems are sized based on settling velocity of grit. Settling velocity varies based on size, shape, density, etc. A major reason that conventional grit removal systems do not work is a lack of understanding of how municipal grit actually behaves. Since grit is not well understood, it is often erroneously treated as clean sand particles. This is a major reason why most grit removal systems fail to capture the quantity and sizes of grit they are designed for. Understanding the actual characteristics of grit at a particular location helps determine the sizes and types of grit removal system that is needed to remove it. Here are some magnified pictures of pure silica sand on the left and municipal grit at the right. As you can see, silica sand has well-defined geometry, whereas wastewater grit, wrapped in fats, oil, grease, and organics, has irregular shape. Therefore, it has irregular densities, and therefore, it would have different settling velocities compared to pure silica sand. The fact is that wastewater grit is very different to an ideal silica sand. An easy analogy would be that of falling rain versus falling snow. Furthermore, most grit is smaller and lighter than the standard against which conventional equipment is designed. As we saw, there are variations in types of grit. Municipal grit is not just a clean 200 micron spherical silica sand. Systems also have to deal with non-uniform particles, varying sizes, and addition of biomass. Variation in grit causes variation in settling velocities. With attached biomass, larger grit particles settle at slower rates. A 200 micron particle with a layer of fat may settle like a 75 micron particle. So if a system is sized for a 200 micron clean grit, it might not even capture a 200 micron municipal grit, at least not the bulk of it. Another problem when sizing to remove 200 micron grit is that sometimes that is not enough. This is a compiled particle size distribution curve of the grit from 18 different plants in the US. In almost all of them, you will find that sizing to remove 200 micron grit particles will only remove 50% of the total grit load. If we modify our design criteria to remove 90% of the total of the incoming grit, then we need to change our design cut point to somewhere between 70 to 150 micron, depending on the endemic grit gradation. This is the grit distribution curve of a grit that was found in the aeration tanks in a plant in US. This was downstream of a mechanically induced vortex grit removal system, and this still had a lot of grit. Almost 45% was 300 micron, which that technology said it would remove 95% of. Obviously, that did not happen. You can also see that there were a lot of fine grit. Almost 53% of grit was less than 200 micron. Because grit is affected by size, the shape, the specific gravity, and then also what it is exposed to in the collection system, like fats, oils, and grease, dissolved gases, all sorts of material, then can attach to the grit particle and impact the settling velocity. Very few materials that we would expect to make up our grit load are 2.65 specific gravity. These are specific gravities of various materials that very likely are part of your grit makeup. Actual plant data from a couple of SCPs show grit specific gravity of 1.3 to 1.5. And these plants found that larger grit particles were very flat shaped and they settled the slowest. And that's important because it takes 100 micron silica sand particle of 2.6 specific gravity 38 seconds to settle, whereas it takes a particle that has 1.35 specific gravity almost 4 times longer to settle. So it is important to understand your grit. And once you understand your set velocities, you can assign what's known as sand equivalent sizing. So if a clean sand particle settles quickly, represented by the long arrow, but the same size municipal grit particle settles more slowly, we can normalize the grit settling velocity based on a known quantity of sphere silica sand. We can say that this smaller sand particle settles at the same velocity as the larger municipal grit particle. And then we design to remove the smaller clean sand particles, which remove more slowly settling grit particle. SES, or sand equivalent sizing, is now referenced in Metcalfe and Eddy as well. So where is all this grit coming from? Grit remains in the collection system until it is transported to the plant. Low flow moves only small and light grit. Increased flow suspends the grit. First flush or peak flow significantly increases the grit load. Effective grit removal systems must function at peak flow and peak grit load simultaneously and must not short circuit the flow. So in addition to grit target particles and variation in grit settling velocities, a factor to consider is peak flows. These are some estimations that we have collected from different regions in which we operate. A peaking factor of 2 can increase the grit load by 10 times. A peaking factor of 4 can increase the grit load to 20 times. Most grit removal systems are not designed to handle such varying grit loads. So this is why conventional design wisdom doesn't work. It targets much larger particles than it should to effectively capture the grit that is covered in fats and organics, and does not take into account the effects of peak loads, the shape, the size, or specific gravity. So less than 50% capture of settleable grit is not good enough. Our conventional design criteria has been to target the big grit, 210 microns and larger, with a specific gravity of 2.65. Historically, we focus on larger grit so that we would not retain organics, which create odors, increases volume and water content, and can make the product unacceptable at a landfill. We as an industry have never taken much more than a cursory view of our grit removal design criteria or characteristics, of which the grit entering wastewater treatment plants. As we move towards higher performing processes, effective grit removal will become more important criteria in our treatment plant designs. One certainly does not want grit entering an MBR plant where it can abrade the very expensive membranes. We have already seen that in one of our projects, where the owner refused to allow any product that does not guarantee fine grit removal, as they had sensitive membranes downstream. Centrifuges operate at high speeds, which accelerate abrasive wear. Even as we upgrade from coarse bubble aeration to fine bubble aeration, the potential for grit deposition increases as the scouring velocities in the basins are reduced. Should this be considered routine maintenance then? Or should we be able to protect the plant from grit? We can manage it in the headworks where it's easy, or manage it in the rest of the plant. For a grit removal system to be effective, it must target finer particles. It must take into account the variation in grit size, and it must be designed to suit peak flow and peak grit loads. And we can help you with that. To help you save maintenance costs, Hydro International offers grit removal systems that guarantee fine grit removal. The first solution I will talk about today is HeadCell. HeadCell is a stacked tray grit removal system. It offers 95% removal efficiency down to 75 micron target particle size and larger. HeadCell is the only gravity sedimentation technology with such a guarantee. The device itself requires no external power. It has no moving parts, therefore has low maintenance requirements. It is ideal for retrofit applications, and we have over 400 installations as a reference. This is an animation based on the CFD of the HeadCell. The manifold feeds inlet ducts that feed each individual tray. The flow is fed tangentially, creating a vortex. The tray lip keeps the grit on the tray and allows it to be captured in the boundary layer, which sweeps the grit to the center. The grit collected in this grit sump at the bottom of the unit is pumped to washing and dewatering. The degritted effluent is discharged between each individual tray into the surrounding basin and exits the basin over the weir. HeadCell has a robust construction where trays are made of plastic and the support frame is made of 304 or 316 stainless steel. It is installed inside a concrete chamber, either above or below ground level, depending on site requirement and condition. It has a high turndown range, which means it can handle fluctuations between peak and average flow rates. It is always sized for peak flow and grit load, so the grit removal performance is not compromised. It has a relatively low head loss of less than 305 millimeters at peak flows. HeadCell has a significantly smaller footprint compared to other technologies while delivering much better performance. Another product in our portfolio that has excellent fine grit removal performance is GritKing. GritKing can be sized to target 95% removal efficiencies for all grit down to 106 micron. The product has no moving parts and can handle wide ranges of flows. The inflow and underflow can be gravity or pump flow. GritKing produces very low head loss, typically less than 150 millimeters at peak flow. Due to absence of any moving parts, the device is very simple to operate and maintain. The flow enters tangentially into the unit where it is directed in a circular path. This allows the grit an elongated path have more settling time. The grit is collected at the bottom in the sump from where it can be extracted by either under gravity or pumped extraction. The second spiraling column takes the treated effluents towards the overflow channel. The GritKing can be designed inside a concrete chamber or as a standalone vessel to suit the hydraulics of the plant. The image on the left illustrates a freestanding configuration. The image on the right illustrates an in-situ GritKing arrangement which features a submersible pump for further flexibility within a concrete chamber. This flexibility and ease of installation makes hydro solutions simple to design into your works. The GritKing 2 is substantially smaller than its rivals, with typical land requirement less than 50% of those required for other solutions. The layout and handling of the process can also be tailored to the site, as there are no requirements for long straight inlet channels in set orientations. Let's compare the conventional technologies with Hydro's grit removal systems. The source of the removal efficiency data for other technologies is taken from independent research paper. The detritus tank did a good job by removing 57 to 68% of all grit, 106 microns and larger, but it was running only at 66% of design flow. The aerated grit basin, when it was running at 66% design capacity, also had good removal of around 67%. But when it received flow at 100% of the design capacity, the removal efficiency dropped to 32%. That is not going to protect the plant when you're having peak flows. Mechanically induced vortex or impeller-driven systems at 27 to 90% design flow generally showed around 50% removals of 106 microns or larger. Both our units, the HeadCell and the GritCleanse, at 100% of the design flow showed between 87 to 93% removal efficiencies. These claims have been proven many times, and we'll be happy to share more details about our performance. We can help you get from this to this. The picture on the left is from a plant that had an underperforming grit removal system, showing collection of grit in an oxidation ditch. The grit reduced 18.6% of the treatment volume in 5 years, cost them around $200,000 to clean up. On the right, you have an oxidation system from a different plant, which is protected by Hydro's HeadCell grit removal system. This is what they found after 3 years of operation, virtually no grit. The difference is quite clear. I do not know any operator or owner that wouldn't be happy with this. We've talked about the grit collection step and the importance of targeting fine and light grit in order to more effectively remove grit and minimize deposits. We have targeted fine and light grit material. We will also retain more organics. So we need to look closely at washing and dewatering and do these steps as well as the grit collection system. So finally, I'll talk about grit washing and dewatering system called Hydro GritCleanse. Hydro GritCleanse is a fluidized bed grit washing system that significantly reduces volatile solid content to produce cleaner, drier wastewater grit, reducing volume, weight, and water content to reduce odor issues and reduce landfill disposal cost. GritCleanse is designed to receive underflow grit slurry from GritCleanse or HeadCell to wash and dewater the grit. It produces greater than 85% total solids and less than 5% volatile solids. Usually has an intermittent operation is preferred, and as it reduces energy usage and improves GritCleanse efficiency. The maximum solids handling capacity is of 1.14 cubic meters per hour. To summarize, I would say that effective grit removal system can save wastewater treatment plant significant sums of money. I hope this presentation was useful to you. If you have any queries or questions, please don't hesitate to reach out to us at skhan@hydro-int.com. There's a short survey after the presentation, so please, we request you to please participate in that survey. Thank you.